ganglia and limbic lobe. Historically, the basal ganglia are considered as major components of the motor system. Their relationship to movement is best understood aspect, which shows up clinically in disorders like Parkinson's disease and Huntington's disease. The meaning of the term basal ganglia has changed over years. Most agree that there are 6 major structures: caudate nucleus, putamen, globus pallidus, nucleus accumbens, substantia nigra, and subthalamic nucleus. Caudate nucleus and putamen have similar and parallel connections and are referred to in combination as corpus striatum. Putamen and globus pallidus have different connections but are physically stuck together. In combination, they are referred to as lenticular nucleus. Nucleus accumbens. Nucleus accumbens is only found at the most anterior part of the basal ganglia. It is identified as congruent between the putamen and caudate nucleus. Caudate nucleus. It parallels the lateral ventricle. It has an enlarged head in the wall of anterior horn, a small body adjacent to the body of the ventricle, that is lateral ventricle, and a smaller tail adjacent to inferior horn of lateral ventricle. Caudate nucleus and putamen merge with each other anteriorly, and the area of fusion is nucleus accumbens. Lenticular nucleus, that is, it includes putamen and globus pallidus, underlies insula. Globus pallidus is the more medial. It has 2 parts with distinctive connections: external segment adjacent to putamen, then internal segment closer to thalamus. Substantia nigra. It is located in the midbrain. It extends rostrally into the diencephalon. Substantia nigra is a 2-part structure. Compact part closer to the red nucleus contains pigmented dopaminergic neurons. Then reticular part adjacent to cerebral peduncle and is a displaced piece of GPI, that is globus pallidus internal. Subthalamic nucleus. Subthalamic nucleus is located inferior to the thalamus, just above the most rostral part of the substantia nigra. Basal ganglia have no major outputs to lower motor neurons. They work primarily by influencing the cerebral cortex and play a role in the initiation of movements. Input and output. Striatum is a major input part of basal ganglia, collecting excitatory inputs from large cortical areas. The GPI, that is globus pallidus internal, and substantia nigra reticular are the principal output structures, sending inhibitory projections to the thalamus, which in turn project to the cortical area. All connections are ipsilateral. All structures and their connections are pertaining to one cerebral hemisphere. So damage to any one of them results in contralateral deficits. Caudate nucleus receives its input from different widespread area of the cortex. It influences globus pallidus, which in turn projects to the thalamus and its own restricted cortical area. Putamen is directly involved in the movement disorders. Its inputs come from the motor and somatosensory areas that are flanking the central sulcus. Its output reach motor areas of the cortex, particularly the supplementary motor area, by way of ventral lateral and ventral anterior nucleus of the thalamus. Putamen and supplementary motor areas are involved in planning and initiating voluntary movements. Dopamine. Dopamine projections from substantia nigra and from ventral tegmental area, that is to the nucleus accumbens, are important category of striatal inputs. Disruption of the dopamine from substantia nigra compact causes Parkinson's disease, and the disruption of the dopamine from the ventral tegmental area, that is nucleus accumbens, alterations in the motivations. So, globus pallidus internal and substantia nigra reticular, different parts of striatum project to particular parts of globus pallidus, both segments, and also substantia nigra reticular. The GPE external sends inhibitor projections to most other parts of the basal ganglia, whereas the globus pallidus internal and substantia nigra reticular provide the major outputs from the basal ganglia. Pallidal output fibers, that is from GPI internal, reach thalamus through two bundles. One is direct pathway, that is ansa reticularis, hooks around the medial edge of internal capsule, and lenticular fasciculus passes directly through the internal capsule. Two bundles join and form the thalamic fasciculus, which then synapse into ventral anterior nucleus of thalamus. The cortex, striatum, GPI and substantia nigra reticular thalamus cortex loop is often considered to be the direct pathway through basal ganglia that facilitates movement. A circuit whose malfunction partially explains the slow and diminished movements of Parkinson's disease. Indirect pathway. Striatum is a major source of inhibitory input. Subthalamic nucleus, on the other hand, provides powerful excitatory input. Subthalamic nucleus is often considered to be part of an indirect pathway through the basal ganglia, one that has such opposite effect on thalamic activity as the direct pathway. The basal ganglia disorders are characterized by combination of both positive and negative signs. Positive signs being involuntary muscle contractions in various patterns. Negative being difficulty initiating muscle contraction. Parkinson's disease. Parkinson's disease is a classic example. Positive signs include resting tremor, especially pronounced in the hands, and a general increase in the tone in all muscles referred to as rigidity. Negative signs include slow movements, that is bradykinesia, and a reduced number of movements, that is hypokinesia or akinesia. Parkinson's disease is characterized as a loss of dopamine neurons projecting from the substantia nigra compact to the striatum. Huntington disease. Other basic ganglion disorders such as Huntington's disease can be accompanied by different kinds of involuntary movements that fall into three general categories. Rapid movements called chorea, slow writhing movements called erythrosis, and flailing movements of entire limbs called ballism. Huntington disease is caused by autosomal dominant mutation. This results in a more selective loss of striatal neurons in the indirect pathway. Then we go to limbic lobe and connections. Parts and major components of limbic lobe. The limbic lobe, it is a complex region and includes cingulate gyrus, parahippocampal gyrus, hippocampal formation, subcallosal gyrus, para-olfactory gyrus and pre-terminal gyrus. Cingulate gyrus is located above the corpus callosum. It continues posteriorly and it follows the curvature of corpus callosum, dips beneath the splenium to continue anteriorly as isthmus of the cingulate gyrus. Anterior continuation of the isthmus is the parahippocampal gyrus, whose anteriormost extent is known as the uncus. Beneath the rostrum of the corpus callosum is the subcallosal gyrus. Connection between the anterior commission and the optic chiasma is the lamina terminalis. Cortical tissue anterior to the lamina terminalis is the para-olfactory gyrus and pre-terminal gyrus. Subcallosal, para-olfactory, pre-terminal gyri are referred to as subcallosal area. Limbic connections. When we see things around us, we perceive multiple attributes of things. Their physical attributes, whether they are attractive, frightening, and so on. Information about the physical attributes come from unimodal association areas, whereas information about their drive-related attributes comes from the limbic structures. Drive-related attributes of objects or situations have autonomic and behavioral responses, and these are mediated by limbic structures in conjunction with hypothalamus and adjacent septal area. Limbic structures serve as a sort of bridge between neocortex and the behavior when drives and emotions are involved. Limbic system includes both cortical and non-cortical structures and is divided into two subsystems, one centered on hippocampus, other on the amygdala. Each uses different areas of cerebral cortex as a part of bridge to multimodal association areas. Cingulate cortex, it is the gyrus and is a hub that contains both sensory and motor areas and is involved in self-monitoring and decision-making. It is an integral part of limbic system that has reciprocating communication with the hippocampus and multimodal neocortex, playing a role in the process of learning and memory by linking behavioral outcomes to motivation. A certain achievement induces a positive emotional response resulting in learning. Lesions of cingulate cortex. Lesions of anterior cingulate can cause complete cessation of motivated behavior. Nothing in the environment is perceived as important enough for the patient to talk or make a movement. Consequently, the person appears immobile and completely disconnected with their environment. This extreme condition of lack of limbic drive is called as akinetic mutism. Depression is often associated with reduced activity of the cingulate gyrus. Amygdala. It is a collection of nuclei located in the temporal lobe at the anterior end of hippocampus. It receives a great deal of sensory information of all sorts from brainstem, thalamus, hypothalamus, olfactory bulb, and unimodal association areas. It also receives input from anterior parts of limbic lobe and nearby areas including orbital, anterior, temporal cortex and the insula. Its connections with the thalamus travel through both stria terminalis and a more diffuse pathway that passes underneath the lenticular nucleus. Amygdala, it uses its interconnections with limbic and sensory cortex and the hypothalamus, both to and from, to express association between objects and reactions they provoke. That is, while hippocampus is important for remembering an event occurred, amygdala is important for remembering whether the event was good or bad, and also for triggering appropriate responses, gut feelings, the next time a similar event occurs. Conclusion. Emotional experiences are accompanied by conscious awareness of emotion, autonomic reactions, heightened awareness of ongoing events. Outputs from amygdala help mediate all of these. Output from anterior limbic cortex, both directly and through dorsomedial nucleus of thalamus, contribute to conscious experience. Those to thalamus, hypothalamus, and to brainstem, visceral nuclei mediate autonomic responses. Those two sensory cortical areas are extensive than inputs and help to enhance the performance when the pressure is on. Those two sensory cortical areas are extensive than inputs and help to enhance performance when pressure is on. Output to the ventral striatum get the basal ganglia into the act, and outputs to the hippocampus affect the probability that an event may be remembered. Thank you.